In this video, I'm going to focus on the meaning of the gradient. So let's see what we remember from the gradient. So the gradient acts on a scalar field, let's call it phi. You apply the gradient, and you end up with a vector field f. And you already know how to calculate it. You just have to apply the operator nabla to the scalar phi, which means you get a vector whose components are the partial derivative of phi with respect to x, the partial derivative of phi with respect to y, and the partial derivative of phi with respect to z. Importantly, please remember that these are not a scalar and a vector. These are actually a scalar field and a vector field. And what I mean by this is that this is a scalar which depends on position, and this is a vector field, so it's a vector which depends on position. So now my question is, how does f look relative to phi? And for that, I am plotting examples for you. Okay? The first example that I'm going to do is a two-dimensional example in which phi is my vector field, my scalar field, which is the input here. Yeah, so this is the input. Let me actually. So I'm going to plot this input field on an xy plane. So it's a two-dimensional function. And this is how it looks. Okay? So you can see that you have these different values. So you have a local minimum of the scalar here, where it's equal to -1, and you have a local maximum of the scalar here, where you have the scalar equal to 2. And you can see I'm plotting these lines, and these lines represent lines of constant value of the scalar phi. Okay? So if you move along this line, phi is not changing. Okay? These are called the contour lines, as is written here. So that's our input. So what happens if you calculate the gradient of that scalar field? We will get a vector field, which we know how to calculate. So now I asked the computer to calculate this vector field and to plot it. Okay? So the vector field will be a vector field, which means that at each position x and y, we will get a vector. And that's what I'm plotting on the right here. So I'm going to plot it here. So this is the vector field f. And I'm plotting this vector field using red arrows. But I am actually plotting the red arrows on top of the scalar field so that you can compare both fields at the same time. So you can see that at each point x and y, you have an arrow, okay, as expected for a vector field. And how does the vector field look like? Well, it looks pretty interesting, right? So if you are at the minimum or at the maximum, it seems that this vector field is 0 because the length of these arrows is 0. While here, the length of the arrows is clearly much stronger, much longer, right? Also, the arrows, they seem to be pointing in the direction in which the scalar field is increasing, right? And this is what happens with the gradient. It is actually even easier to visualize if we make use of 3 dimensions to plot this. Since our scalar field is a 2-dimensional field, which is defined in x and y, we have one axis, the z-axis, we have it left. So we can use the z-axis to plot the scalar field, okay? So that's what I have done here. So here I have the x and y axis over which the field is defined, and I'm using the z-axis to plot the value of the scalar field. So you can see you have the local minimum and the local maximum, which is now very intuitive to see. And now I'm going to add the gradient of this scalar field using arrows. And now you can see how nice this is. So clearly these arrows are pointing in the direction of steepest ascent. So which is the direction in which the height will increase the fastest. Yeah. So if you are standing at any point and you follow the direction of the arrow, that's the steepest direction. Okay? Also, the length of the arrow depends on how steep that slope is. So for example, from here to here, clearly the slope is not as steep because the length of the arrows is smaller than if you try to go from here to here, when the slope is very steep, and so the length of the arrows is very long. Okay? So let me summarize those two things. So the length So at each point x, y, z, the length or norm of f, which is the length or norm of the gradient of phi, tells us how fast the scalar field is changing. While the direction of the vector f, let me write of the vector, which is equal to the gradient of phi, the direction of this vector tells us the direction of steepest ascent. Okay, it's remarkable how such a simple operation can tell us so much about this scalar field, right? It's almost magical. That's the beauty of maths. Sometimes with very simple operations you can do really cool things. One thing that I would like to note, and I will justify it later, is that the gradient, the direction of the gradient, if you look at it, it is always perpendicular to the lines of constant scalar field. So it's always perpendicular to the contour lines. So for example, here, the gradient is pointing in this direction, and the contour line is this one, and this is perpendicular. So this always happens at every single point. Notice here, you have this line of contour, and the gradient is pointing in this direction, and this is perpendicular. Okay, and I will justify it later in the next video. So I can add that. The direction of the vector of the gradient is always perpendicular to the contours of constant phi. Okay, this is also true in 3 dimensions. So although here I drew a 2-dimensional example, I can also do a 3-dimensional example. And for this I don't have a nice Mathematica figure, but I can try drawing it myself. So what is an example of a 3-dimensional scalar field? For example, the temperature of a room as a function of position. We can calculate the gradient, and we will get a vector field. And let's see how this would look like. So for example, imagine we have a room in whose ceiling we place a very hot light bulb. So here in the ceiling we place a very hot light bulb. Let's say this light bulb is at 100 degrees or whatever. And now I ask you, okay, how is the temperature distribution in this room, the scalar field of the temperature? So clearly the temperature is going to be higher here, and it's going to get cooler and cooler as you move away from the bulb. So now instead of drawing contour lines in which the temperature is constant in a 2-dimensional scalar field, now in 3 dimensions this becomes contoured surfaces. So for example, which points of the room are at 90 degrees? Those will be points that are relatively close to the light bulb, right? So you can imagine you have some surface here surrounding the light bulb. So this is a surface, 3-dimensional surface that surrounds the light bulb where the temperature is at 90 degrees. Okay, then you could draw a surface where the temperature is at 50 degrees. And so on, you can keep drawing these contour surfaces in which the temperature is constant. Okay, so then the gradient field F, so this F, will be a vector field such that at every point in the room you will calculate a vector, which is the gradient of F, and it will be always perpendicular to these surfaces, and it will point in the direction of steepest ascent. So what's the direction in which the temperature is increasing the fastest? Yeah, and this will be a vector field defined for every point in the room in three-dimensional space, and this will be the gradient. Okay, so I hope you now have a very good intuitive picture about what the gradient is. See you in the next video.